So we'll start the session now. So good evening, everyone. This is live discussion session number 3 for the NPTEL course entitled Basic Thermodynamics, Classical and Statistical Approaches. So I will introduce first myself. Myself Akash Gutal. I'm a PhD student from Department of Chemistry in Indian Institute of Technology, Jodhpur. So today, before going to the problem section, we will do one quick revision about what we have done last week. So initially we have started, that is, what is the work done at constant temperature. So the work done at constant temperature is nothing but W is equal to minus P external dV, and then it followed by constant temperature quasi static work, which can be given as W is equal to minus nRT ln V2 by V1, which is also called isothermal reversible process. Fine. After that, we started about heat. So heat is, as we know, heat is a path function, and which can be expressed as the multiplication of specific heat into change in temperature. Okay, dt, change in temperature. So, and after that we have seen the change in internal energy, change in the internal energy at constant volume. Okay, the change in internal energy at constant volume, we have given that it's CV d dV, right? And this expression is true for all gases. Right? So after that, we defined what is the enthalpy. Definition sorry definition of enthalpy. So H is nothing but U plus PV. So it can be called as heat content sorry It can be called as heat content of the system. Fine. So what is the enthalpy? And its mathematical, the change in enthalpy mathematically can be given as Cp into T2 minus T1. Fine. And we know after that we have calculated what is Cp minus Cv. The expression for Cp minus Cv can be written as del V by del T at constant pressure and del U by del V at constant temperature plus P. So this is the expression for Cp minus Cv. And we have seen that for ideal gas, Cp minus Cv is nothing but an R. It's for ideal gas. Fine. Then we have seen Joule's free expansion. So what is the Joule's free expansion? And we in Joule's free expansion, we defined what is the Joule's coefficient, which is nothing but del T by del V constant entropy at constant internal energy is minus 1 by Cv del U by del V at constant temperature, which ensures you that del U is 0. So this is called as Joule's coefficient. Fine. So then we have seen what is the Joule-Thomson effect. I can write it here. So we have seen what is the Joule-Thomson effect. For Joule-Thomson, we have calculated for Joule-Thomson effect, delta H is actually 0. So in case of Joule's free expansion, we have internal energy change is 0, and in Joule-Thomson effect, we have change in enthalpy of the system is 0. So in that isoenthalpic process, we have defined what is the isothermal Joule-Thomson coefficient is nothing but del H by del P constant temperature. So is called as isothermal Joule-Thomson coefficient. Fine. And after that, we found that the actual Joule-Thomson coefficient is denoted by mu, and it's having relation between the isothermal Joule-Thomson coefficient is Cp minus Cp into U is del H by del P constant temperature, and this is nothing but it gives you 1 minus 1 by Cp del H by del P constant temperature, and it's actually defined as change. So I will write it in front of this here. Mu is actually del T by del P at constant enthalpy. And we know that mu is equal to 0 for ideal gas. Fine. After that, we have defined the same Joule-Thomson coefficient for real gas. For real gas, so we know that del H by del P at constant temperature for real gas is del V by del U by del V, that is internal pressure, plus P into del V by del P at constant temperature, plus CV del T by del P constant temperature plus P. Fine. And what we know that internal pressure is nothing but T into del P by del T into V minus P. So what we have this internal pressure, we will get this expression in second law of thermodynamics. So in future we will have the derivation of this expression, and which gives you del H by del P at constant temperature is T into del P by del T constant volume, del V by del P constant temperature plus P. This expression for del H by del P at constant T. So we have seen that for real gas such that it which follows the van der Waal equation, what we know that this del H by del P value is turned out to be B, which is nothing but isothermal Joule-Thomson coefficient. It turns out to be B, and we know the Joule-Thomson coefficient is equal to minus of 1 by Cp into mu T, which gives rise directly gives us the fact that is Joule-Thomson coefficient for real gas, which follows the van der Waals equation, is nothing but minus B by Cp. And this is for when we keep the A coefficient as 0 in van der Waals gas. So because of that, as a definition, as we have the definition of mu, it's del T by del P at constant temperature, at constant isoenthalpic process, is actually we can express as del T by del P is from this expression, mu is negative, which means this value is negative, and del T by negative P, it's proportional to the negative P, which means is that once the pressure is decreased, the temperature will increase. When the expansion is happening, the gas will, when gas get expanded, real gas get expanded, its temperature will increase. And this is for again we consider A is equal to 0 in our real gas van der Waals equation. After that, we discussed what is the adiabatic reversible work. So for adiabatic reversible work, P raised to P, we found that PV raised to gamma is equal to constant. So this expression can be written in two different ways. In terms of TV is TV raised to gamma minus 1 is constant, and in terms of PNT, PT gamma upon 1 minus gamma is constant. After that, we find out the work done adiabatic can be given as minus P1 raised to gamma 1 minus gamma into V2 1 minus gamma minus V1 raised to 1 minus gamma is equal to CV T2 minus T1. And at the end, I would like to define some three new quantities which are essential in competitive examinations. So these are, first one is isothermal compressibility, which is denoted as kappa T, kappa T, and this is also T. Its expression is minus 1 by V del V by del P, constant temperature. And the same thing we can write for isobaric thermal expansivity of a gas can be given as, and that is denoted, and the coefficient related to is denoted as alpha, which is alpha can be given as alpha is equal to 1 by V del V by del T at constant pressure. Okay? And at the end, uh, in problems we will always see the word internal pressure, which nothing but the value del U by del V at constant temperature. So what this means, this means that the for change in small change in volume, the change in internal energy is actually having dimensions of pressure, and because it's related to internal energy, it's called as internal pressure. Right? So we will move towards problem. So we will see how to solve it. So once you see this reaction, as you can see, you when you see the reaction, you should see what is the uh, volume change during this process. So you can get the information, thermodynamic information, when you check the volume change inside the system when the reaction happens. So SO2 is nearly, it's 1 mole, which means, let's say, is 1 volume. And fine, it's fine, you can follow. We will solve nearly 20 problems. Uh, I have collected it from different sources. You can actually follow me while I am solving. I will solve one by one. You can, yeah, fine. So this will be half of the volume, and what it is happening is when SO3 is get formed, it is only one volume is formed. Fine. So what is happening? What the reactants are having 1.5 volume, which is converting into only one volume. So what is happening when you are, if it is a reaction chamber, so there is SO2 and half O2, When reaction happens, there is external pressure. And the reaction happens, and this half volume will convert it into uh, reduces, and this piston will get uh, compressed. So the system get compressed when there is formation of SO3. Fine. So this was the previous condition. Let's get compressed. So what we know, so what is happening here, the work is done by the external pressure on the system. So when work is done on the system, whatever the work uh, has happened, it will go according to first law. We know that the work will go inside the system, that is du dq plus w dw. So we don't know what is the dq, but we know the work is done on the system. Once it is done on the system, then the temperature of the system will increase. Once the temperature is increased, means internal energy will increase, and the reaction become exothermic. So hence the reaction is exothermic. Yeah, yeah, right answer, Ankita, right. Okay, the second, let's move towards second question. So keep your pen and paper ready, try to solve it. So the question is, calculate the Q and W for the isothermal reversible expansion of the 1 mole of an ideal gas from an initial pressure of 2.0 bar to a final pressure of 0.2 bar at constant temperature of 273 Kelvin. So we need to find out Q and W. So it's given that it's isothermal reversible expansion. So we'll take out what things are given. We need to find out Q and W. Fine. And the N is number of mole is 1. Ideal gas from initial pressure is given 2 bar, which is P1 is equal to 2.0 bar, and the final pressure of 0.2 bar. P2 is 0.2 bar. And what we have, the temperature is 273 Kelvin. Right? So we know what is the isothermal reversible expansion minus nRT ln V2 by V1. But its pressure is given. So we know for ideal gas, pressure is inversely proportional to the volume. So we keep it ln. So it will be P1 by P2 because it's inversely proportional. If you put things, it's minus 8.314 into 273 and ln P1 by P2. P1 is 2.0, P2 is 0.2. So can you calculate this? So if you calculate is W is equal to, comes out to be minus 5226.228. Fine. So as it is isothermal process, from the first law, we know change in internal energy will be 0 because the temperature is constant. Because of the temperature is constant, the change in internal energy will be 0. And whatever the heat it gained by the system is actually, yes, 5220.25. Right answer. So the answer should be The answer should be, as we know, dq is minus dw. That's it. Once you know the w, dq will be the reverse of it, reverse sign of it. Just reverse the sign, the same the answer. Answer is B. So third question is a sample of an ideal gas. Gamma is given 1.4. Is heated at constant pressure. If 140 joule of heat is supplied to gas, delta U and W respectively will be. Let's try to work out. This is also related to the first law of thermodynamics. So there is no need to calculate delta U and W separately, because not that much information is given. You can tally it from the options itself. So what we have, first law of thermodynamics, change in internal energy is nothing but heat absorbed by system plus the work done by the system, or work done on the system. So what we know is the heat given to the system is 140 plus dw du. Then we will be having 140 is equal to du minus dw. So which combination gives you the 140 is the answer. The answer should be A. If you put 60 minus 80, that will give you actually the answer 140. Fine. So the next question is, suppose 14 gram of oxygen at 0 degrees Celsius and 10 atm pressure is subjected to a reversible adiabatic expansion to 1 atm pressure. The work done is. So it's a reversible adiabatic expansion. So we'll first take out what things are given. So the weight of oxygen is 14 gram. Let's convert it into number of moles, 14 by 32. Okay. And we have given that pressure is 1 atm. Sorry, the pressure is 10 P1. The initial pressure is 10 atm. And the final pressure that we are going to get is 1 atm. And the temperature is given 0 degrees Celsius means 273 Kelvin. So we know that O2 is actually a diatomic gas. So for diatomic gas, we have gamma is equal to 1.4. Fine. And we know P1, P2. So what we need to do is the work done. What we know is nothing but change in internal energy. Okay, for adiabatic process. NCV T2 minus T1. Fine. So uh, sorry, what we need to know is what is the T2. Okay. So we have P1, P2 and T1. We need to calculate T2. So as we know, we have seen previously that the relation at adiabatic reversible process, the relation between P and T is Pt raised to gamma upon 1 minus gamma is constant. Fine. So when you put, so P1 by P2 is equal to T2 by T1 raised to gamma 1 minus gamma. Fine. Then if we reverse it, we need we need to calculate T2, P1 by P2, 1 minus gamma upon. Let me introduce one new slide. Fine. Or otherwise, or I can do it. So P1 T2 by T1 is, we can do it here. P1 is 10 upon P2 is 1 is 2. Gamma is 1.4 divided by 1.4. It's nothing but T2 is equal to 10 raised to 0.4 divided by 1.4 into T1. So we calculate it. So what T2 will get? Can you calculate? Just try to calculate. 141.4 Kelvin. And this will be the second temperature. So we know T1 and T2. So we can put into this expression and we will get the work done. So work done is equal to the expression we have NCV T2 minus T1, and that we have calculated. Let's keep directly 14 by 32 into CV. So the CV for diatomic gas is nothing but pi by 2 R. Fine. R is nothing but the 8.314 cross T2 minus T1 is 141. Oh, sorry. 0.4 minus 273. So what we will get? The work done that we will get is minus 1196.69. So this is in joule. Fine. We know that 1 calorie is equal to 4.18 joule. So we can convert it into calories. We just need to divide by 4.18. So what you will get? 286.29 calorie. So the closest answer is option number A. Fine. So the next problem is a sample of argon gas at 1 atm pressure and 27 degrees Celsius expands reversibly and adiabatically from 1.25 dm cube to 2.50 dm cube. The enthalpy change in the process is and it's actually CVM is given to you. Okay, it's not that the process is the CVM is not, it's coming after the is, but it is given to you. The CVM value is given to you. Fine. So you need to calculate the enthalpy change in the process. Sorry. This is this is good. A very tricky question. It's simple, but it is numerically layered. It's a little tricky. So we will separate what things are given. So it is given that the pressure P1 is 1 atm and the temperature is at 27 degrees Celsius. Let's convert it into Kelvin. It's 273 plus 27, nothing but 300 Kelvin. And it expands reversibly and adiabatically from V1 is given 1.25 dm cube and V2 is given 2.50 dm cube. And we have been given this CVM for the gas is 12.48 joule Kelvin inverse mole inverse. Right? So if you notice inside this problem, we have not given this number of moles. So we need to calculate the number of moles using ideal gas equation. Okay. So let's calculate first what number of moles this system is talking about. N is equal to, we know that PV is equal to nRT. Take the initial conditions. The initial conditions are, and from this we will N is equal to PV by RT. Right? So your P1. So we have initial conditions that P1 and V1 and the T1. We have all three. We can calculate the N. So the P1 is 1 atm into the volume is 1.25 dm cube. And if we do R in terms of liter atm is 0.082 cross 300 Kelvin. Right? So if you do this, you will get it is nearly 0.05 moles. So we have been asked for calculating delta H. To calculate delta H, what is the change in enthalpy? We know the change in enthalpy is nothing but N into Cp into T2 minus T1. Fine. So what we need to calculate now is the temperature. What is the second temperature? We know the T1. Sorry, we know the T1. We need to calculate the T2. And as it is a reversible and adiabatic process, we know the relation. We have V1, V2. We have T1. We need to calculate the T2. So the relation between in adiabatic process, the T and V is TV raised to gamma minus 1 is constant. So using this expression, we can calculate what is the T2. Let me add one more slide. So we have TV gamma minus 1 is constant. So we know T1 by T2 is equal to V2 by V1 raised to gamma minus 1. So we have V2 and V1. So let's find the expression for T2. T2, if we multiply, and this will be V1 by V2 divided by gamma minus 1 if it comes in this side into T1. Fine. So if we have is V1 is 1.25, V2 is 2.5. So gamma minus 1, T2 is 300 Kelvin. But we don't know what is the gamma. So to know what is the gamma is, but we know CV. CVM is given 12.48 joule per mole per Kelvin. So from that, we know standard for the ideal gas, as we are talking about considering the argon gas as ideal. We know CV, Cp minus Cv is equal to R. So we can calculate Cp is equal to R plus Cv. So nothing but 8.314 plus 12.48 joule mole inverse Kelvin inverse. Fine. So it turned out to be Cp is nothing but 20.794 joule mole inverse Kelvin. Remember, this Cp will also need this Cp in this expression. Okay, and the gamma is nothing but Cp by Cv. What we will get is 20.794 divided by 12.48. So if you calculate it, is nothing but it comes out nearly 1.66. Okay, so you can use it here. 1.25 is 2 times of 2 times of 1.25 is 250. It will be 1 by 2. It's nothing but 0.5, and gamma minus 1 is 1.66 minus 1 into 300 and This will be 0.5 into 0.66 into 300. So can you calculate the T2? So if you calculate this T2 value, T2 value comes out to be 189.986 Kelvin. So we have Cp, we have T2, we have this T1, we have and the number of moles we have here N. Fine. You can put it and calculate the enthalpy change. The delta H will be NCP T2 minus T1. What we get is 0.05 into Cp. I think we have covered 20.794 into 186.86 minus 300, which in turn give. Can you calculate? Just calculate if you have the calculator. I will give you 2-3 minutes. Just calculate it. The thing is that, so in this example, if you see, many things are not known. You need to calculate. So in case of problems in thermodynamics, what you need to do is there are hidden things. Information is given inside the problem. So here we calculated the N value, number of moles, and the T Cp that we have calculated for the from the given information, and the temperature too we have calculated. So you need to, and gamma also. So these are the hidden variables you need to take out from the given information. So the answer that you should get is minus 114.551. Fine. So what this is actually T2 minus T1. If you'll get the idea, is this is the negative value, and the only option is negative is, even if you don't need to calculate, only option negative is the option number A. Fine. Let's move towards next problem. The problem goes like this: a vapor at 22 atm and 5 degrees Celsius was allowed to expand adiabatically to a final pressure of 1 atm. Temperature fell by 10 Kelvin. Calculate the Joule-Thomson coefficient mu at 5 degrees Celsius, assuming that it remains constant over this temperature range. So let's take out what things are given. So we have P1 is equal to 10 to 2 atm, and the in question is it's told that expand adiabatically, and the final pressure is 1.0 atm, and temperature is actually fell by 10 Kelvin. So it's given that delta T is given, not T is given. It's delta T is 10 Kelvin. Fine. It fell means it, and we need to calculate Joule-Thomson coefficient mu at temperature 5 degree Kelvin, 5 degree sorry Celsius, and it is assumed that mu remains constant over temperature range. Fine. So by definition, what we know is by definition is for of the Joule-Thomson coefficient, change in temperature, change in pressure as isothermal process. Fine. So we know that delta T is given as 10 Kelvin. Okay. So this expression we can write it as delta T for sufficiently large change. Delta T is given 10, and the pressure and the change in pressure. So we need to calculate change in pressure. P1 and P2 is given. So what is the change in pressure is P1 is 1. It's a 22 minus 1. Change in pressure is given as is nothing but 10 by 21. If you calculate what is the 10 by 21, number 0.476, and can be write at 0.4 8 atm. What is the answer? Answer will be B. Fine. Yes. Okay. So seventh question is a gas obeying the equation PV minus NB is equal to nRT is subjected to a Joule-Thomson expansion. The temperature of the system will increase, decrease, remain constant, either increase or decrease. So this question we have seen, actually this we discussed in the revision part also. So this is the gas equation is given, P into V minus NB is equal to nRT. Fine. So this is something like van der Waals gas equation, where A is 0. Okay. And we as discussed before, as we discussed before, that let me go here. Yeah, here we discussed that that van der Waals gas, when A is equal to 0, we know that mu value is minus B pi Cp. It's a negative value. So if it is a negative value, this question is related to the same. Here the same condition will be there. Mu is actually negative, which means del T by delta P is actually negative, and we know delta T is negative delta P. So what we consider here, what is happening here is Joule Thomson expansion is happening. When expansion is happening, something is expanding, which means its volume is increasing and the pressure is decreasing. Okay, the pressure decrease is happening. So when the pressure decrease is happening, so we have the relation when the pressure decreases, as it is a negative value, the delta T is actually increases. So this actually what delta P gives you is negative value, and negative will be positive, and your overall delta T will increase. So your answer should be, it must increase. Yeah, good. Next question number 8. So we have given that mu is equal to 1.11 Kelvin per atm for carbon dioxide. Calculate the value of its isothermal Joule Thomson coefficient and calculate the energy that must be, it is that, okay, that must be supplied as heat to maintain a constant temperature when 12.0 mole of CO2 flows through a throttle in an isothermal Joule Thomson experiments, and the pressure drop is 55 atm. So mu is given. So here I would like to, there is a requirement, there is one requirement which is not given in this particular problem. The Cp for CO2 is 37.35 joule mole inverse Kelvin. So take this, considering this value, calculate the things. And take into mind that mu at isothermal condition, that is isothermal Joule Thomson coefficient, is nothing but mu T. Okay, mu T, and this is equal to, the relation is minus Cp into mu. Okay, now you can able to relate. So you can easily calculate it. So this mu is uh, actual Joule Thomson coefficient, and mu T is nothing but actual is isothermal Joule Thomson coefficient. So we have your expression that mu is equal to minus 1 by Cp del H by del P at constant temperature. So how you understand uh, the isothermal Joule Thomson coefficient is that this part where we can see a subscript temperature is constant. So the word isothermal we know. So this part is isothermal, which means, and we can consider this is mu T. Okay. So whatever you mu have, this is Joule Thomson coefficient. Its standard definition is del T by del P at constant delta. Fine. So your actual equation is del T by del P, constant term P is equal to minus 1 by Cp del H by del P at constant temperature. So what we have, this is called mu Joule-Thomson coefficient, which is denoted as mu. This is called isothermal Joule-Thomson coefficient, mu T. Fine. So if you calculate it, I will calculate this side. Mu is equal to mu T is equal to minus Cp into mu. That will give you 37.35 into 1.11. So what we'll get? Is nothing but mu T is equal to minus 41 point, it comes around minus 41.45 joule atm inverse mole inverse. This is because this 37.35 is approximate. Because of that, it comes different 41.45 something. Fine. So only one option is there, but we will calculate this q also. So what this then what they are asking us is, so what heat must be supplied to maintain a constant temperature when 12.00 mole of CO2 flows through a throttle in an isothermal Joule Thomson experiments and the pressure drop is 55 atm. So what is given here is the pressure is dropping by 55 atm. Okay, let me take one more slide. So the pressure is dropping for, delta P is given is 55 atm. The Joule Thomson coefficient is, and the N is 2, N is 12 moles. And we asked what heat must be supplied. So heat is related to delta H. So they are asking about delta H. Okay, what heat we must supply. So we know that mu T is del H by del P at isothermal at constant temperature. So we can write it at big change del P by delta P by delta P, delta H by delta P, nothing but delta H by is delta P is nearly 55, it's given atm. And what we know that mu T is, we know. So if we calculate delta H is equal to, let me write it in terms of expression. Delta H is equal to mu T into delta P. Fine. So mu T is minus 41.45 into delta P is 55. What you will get is that heat you must supply to keep the temperature constant. Fine. So that comes out to be nearly, if you calculate it, it's 27200. It comes around this value, which is nothing but 1 second. Yeah, it's nothing but 2.7, sorry, 27.2 into 10 raised to 3. in joules. Fine. Answer should be C. So this is the next question. Each of the graphs below has one adiabatic and one isothermal process. Identify the adiabatic process in each graph using the number. So the graph between pressure and volume is given. So and we are asked that what curve identifies what curve denotes the adiabatic process, and uh, these two curves are related to adiabatic and isothermal processes. So we need to identify which one are adiabatic process. Uh, Answer, Ankita, are you telling about C answer? I think the last question, eighth question. Yeah, right. Yes. Try this. So you try this because this doesn't require any calculation. Yes, A. A is right answer. Good. So I will quickly explain what is how we can how we can get the answer. As we know, PV raised to gamma is a constant in case of adiabatic process. Okay, but and in isothermal process we can write it in different way. Let's write P is proportional to 1 by V by gamma, and for isothermal process is 1 by P. Okay, and if you consider the change in pressure and change in volume, del P and 1 by del V raised to gamma for adiabatic, del P 1 by delta V for isothermal. So if I change volume by a small amount, okay, so when you change the small amount, it raised to gamma, and gamma always greater than 1. If it is greater than 1, whatever I value take for del V, it will be enhanced, and once it is enhanced, then the decrease is larger in this case, and in this case the decrease will be not is proportional. Fine. Let me, so we can check whether there is a change in volume. So if you see large change in pressure is happening for this graph, then this, we can say this graph is about adiabatic. And reverse is also true. Fine. Reverse, we can also say the same thing. So the answer should be 2 and 3. The same thing you can draw here. So this will be the less large change, but the less. So this will be 3. This here the pressure will change less. Next question is, given that an ideal gas is expanded from volume V1 to V2 through three different processes: reversible adiabatic, reversible isothermal, irreversible adiabatic, against a constant external pressure P external, identify the correct relation mentioned below. So the relations are given about the final temperature. We need to comment about the final temperature. Just take 2-3 minutes to solve. So from the relation between work done by the gas at these three different conditions, to get we can get the relation between the final temperature. So we know from the discussion that work done by isothermal process is actually highest isothermal reversible process. Answer C. C is also no. Check. Answer C is actually, I think it is not right, because it's irreversible adiabatic both are the same. So you just neglect that option because it's misprinted something. So just take 1 and 2, or 3, 4, 1, 2, 4. So reversible is actually highest work done at reversible adiabatic. So second, and then work done at irreversible adiabatic. So least work done will be by irreversible adiabatic. So how we can comment from having information about the work done, and how we can comment about the temperature. So if you know, it's given that it is ideal gas and the expansion is happening. Okay, the expansion from V1 to V2. When the ideal gas is expanding, when the expansion happens, it means the gas itself is doing work. Okay, and gas is losing heat by doing the work. For the isothermal reversible process, as it is isotherm, whatever gas does the work, the constant heat supply will be there to compensate that work done by the system and to keep the temperature constant. Okay, so suppose we have, this is the temperature T, suppose T initial, and this T remains constant for the isothermal. So T is equal to T final. Okay. The same, suppose we take the same system, if we check the reversible adiabatic condition, having higher work than irreversible adiabatic. Okay. So whatever work in adiabatic condition, whatever system does work, it takes energy from the energy from the internal energy will convert. So in reversible adiabatic, your work is done higher than the irreversible, which means it takes more internal energy. It takes more internal energy from your system, uses more energy from the internal energy, and drops the temperature more. This is a T initial and this is a T final. Yes, temperature decreases. But in case of irreversible, the work done is not that much than the reversible. The change in the temperature will be not that much. This is a T final. Sorry, I need to. Yeah. So we can see the difference. T. So how we can relate these three? TF will be TF of isothermal, reversible, always larger, because at the end the isothermal reversible temperature will be constant. After that, we need to comment about these two. The second highest will be irreversible adiabatic. Okay. Then we have irreversible T final, irreversible adiabatic. And at the end, we'll be having T final, reversible adiabatic. Fine. The option number should be B. Fine. Actually, system will lose the heat, the temperature or decrease in temperature only happens in adiabatic systems. Isothermal is the whatever the temperature initially, that will be stays constant, even though it does more work. So the next question, from this question onward, 10 question I'm taking from 9, I think 9 question. These are from competitive exams. So you can solve these questions also. This is ask this question: if u is a function of v and t, del u by del t at constant pressure is equal to, it's given the pi and alpha are the internal pressure and the coefficient of thermal expansion respectively. This question was asked in CSIR 2016. So we have, I will like to show isothermal, what we have, the internal pressure I defined in the revision section, internal pressure and coefficient of thermal expansion. Coefficient of thermal expansion is the same. Show you the coefficient of thermal expansion. This equation you need to use. Fine. I will write it. I will write internal pressure also. Is nothing but del u by del v. So yeah, at constant temperature. and we have coefficient of thermal expansion alpha is equal to 1 by V, change in volume of the system, change in temperature, constant pressure. Try to work out this problem. The first line is given, u is a function of v and t. From that, you need to extract one thing. You need to write u as total differential form. If you followed the, I think it's second week, the total differential shells are defined. So we know, so we'll write del u as in form of total differential in terms of del u by del v dv at constant temperature plus del u by del t at constant volume dt. So the quantity you are interested in, you need to calculate del u by del t at constant pressure. Fine. So let differentiate left and right hand side using t. So what you will get, and keeping constant pressure, del u by del t at constant pressure will be del u by del v at constant temperature. You will naturally found the internal pressure here. Okay, dv, oh sorry, will become del v by del t constant pressure plus del u by del t at constant volume, and del t by del t will not be, will get cancelled. Okay, del t by del t at constant pressure will be, I will write it like this. This will be no more. This will be 1. So what is the left over? Del u by del t, so pressure. So what you are having here, so this part is your internal pressure, and it's given as pi is internal pressure, and you can put as pi, and this part is del v by del t at constant pressure. So if you have here del v by del t is alpha, in terms of alpha we can write v takes that side, v into alpha is equal to del v by del t at constant pressure. So this is the expression for del v by del t. So write v into alpha, and we know change in internal energy, del u by del t at constant volume is nothing but your cv. Fine. What the expression reduces to? cv, yeah, t plus pi p alpha. What is your final answer? Cv plus pi V alpha. Okay, that's option number 4. This is, I think, 4-mark question. The next question. An automobile tire contains air at 3.20 into 10 raised to 3 Pascal at 20 degrees Celsius. The stem valve is removed and the air is allowed to expand adiabatically against a constant external pressure of 100 into 10 raised to 3 Pascal until P is equal to P external. For air, CVM is equal to 5 by 2 R. Calculate the final temperature of the gas in the tire. Assume ideal gas behavior. So this question was asked in UPSC. I think CSC chemistry paper. Try to solve it. So we'll extract out the given things. This type of question can come in your university exams also. P1 is given 3.2 into 10 raised to 3 Pascal. P external is 110 into 10 raised to 3 Pascal. And it is T1 is given equal to 20 degrees Celsius. So 273 plus 20 to 293 Kelvin. And unit 2 and CVM is given 5 by 2 R. So once CVM is given, CP we can calculate. CP is equal to R plus CV. This is nothing but 7 by 2 R. And again we can calculate gamma value. It's nothing but CP by CV. It turns out to be 7 by 5, which is 1.4. And we have been asked for final temperature of the gas, assuming ideal gas behavior. If the gas is ideal, we know the condition is given adiabatic. We just directly use, we have P1 P2. The final pressure will be P external, P1 P2 and T1 T2. T2 we need to calculate. We know that P into T raised to gamma upon 1 minus gamma is equal to constant. From this expression you can get the answer. So P1 by P2 is equal to T2 by T1 plus 2 gamma upon 1 minus gamma. So what we will get, T2 is equal to T1 cross P1 by P2 1 minus gamma upon gamma, which is nothing but 293 cross 3.2 into 3.2 into 0.4 divided by gamma is 1.4. If you calculate it, you will get T2 is equal to 210.1546 Kelvin. Fine. So adiabatic expansion is happening, which naturally you can tally this answer that the temperature, final temperature must be less than initial temperature because the internal energy is used. Yeah. Question number 13. In an isothermal change, the change in pressure and volume of a gas can be represented for three different temperatures. T3 is greater than T2 is greater than T1. We need to we need to find out which graph is showing it correctly. Remember, this is for isothermal change. This question is from JEE Mains. So why I'm including question from competitive exam, because it tests the concepts. So more concept will be cleared. So try it. So what we have, isothermal condition, P is directly equal to 1 by V. Fine. So, but this expression comes from PV is equal to nRT, ideal gas equation. Okay. P is nRT by V. So here is the T. Here is your T. So if you know the graph of P versus V, so function 1 by V, so this is the 1 by V. How 1 by V varies is like this. Fine. And this T determines its position, whether it is how far away from the origin. So T1, so this is second and this is third. Fine. So the more far away from this origin, the more this nRT value. So this will be the T3. So the greatest will be this T3, then T2, then T1. Fine. D will be the answer. Yeah. Yes, Ankita, it's right. So next question. Heat is given to an ideal gas in an isothermal process. Internal energy of the gas. So 5 statements are given. So whether internal energy of gas will decrease, internal of gas will increase, internal energy of the gas will not change, the gas will do positive work, the gas will do negative work. Choose the correct answer from the options given below. This is simple, right? So 2B and D. Why do you think it's 2? So heat is given to an ideal gas in an isothermal process. So the process is isothermal. Heat is given. So what happens to the internal energy? Internal energy remains the same. Internal energy should be same, because whatever heat you give, that will convert into work, and the system will keep the temperature constant. Fine. So your energy should not change. Sorry. Then next thing, what will happen uh, when the heat is given? This system will do work, and what that work will be? Work will be negative. In the chemistry, we use negative sign for work. So what we have, E and C must be correct. E and C. Yeah, third option. So if you uh, solve this question by using a physics point of view, in physics this work will actually positive, and the answer will be C and D. So don't think about that. It is for chemist. It's C and E. Answer is correct. So the 15th question is the pressure. We have only 19 question. Fine. We will complete, or let's see. We have 10 minutes. Okay. This question is the pressure P and temperature T relationship of an ideal gas obeys the equation Pt square is equal to constant. The volume expansion coefficient of the gas will be. So the volume expansion coefficient we need to find out. So I have mentioned before, volume expansion coefficient in competitive exam. This has been asked for many times. Volume expansion coefficient. This is your volume expansion coefficient. You need to calculate the given information. Pt square is constant. For the ideal gas is given. So this volume expansion coefficient is in terms of V and T. So can we write this expression in terms of V and T? Let's write this expression in terms of V and T. We know PV is equal to nRT. We know that the P is nRT by V. Right? So you can write it as, so this is the constant. It means P is inversely proportional V. So we can write it as in general that nRT by V T square is equal to constant, which gives you T cube by V. If we transfer nR into this side, that will also become constant. This will be constant. T cube by V is constant. Fine. Let's consider this constant as C. Okay. We have T cube is equal to CV. Fine. Now we somehow need to calculate del V by del T. We have CV is equal to T cube. So we can differentiate it. Del V by del T at constant pressure. Let's say, so once we differentiate it, what will we get? 3T square. Okay. 3T square. So we need 1 by V also. We will multiply both side by 1 by V. 1 by V del V by del T, some pressure, 3T square by V. But if you see, the same constant is here. Okay, we can write V in terms of T. okay, for this right hand side. So what it will give you, t square divided by, you can write this c will be the same constant as here, okay. If we can write this v in terms of t, that will be v is equal to t cube by c. If we put t cube by c here, this will be t cube, and c by c means c will get an upper side c. So what we'll get, I will write here c1 by v del v by del t constant p is equal to t square will get cancelled, t 3 by t into c. So c both side will be get cancelled because the same constant is there. Then we will get alpha is equal to 3 by t. Fine. Answer is C. The next question, when 2 liter of ideal gas expands isothermally into vacuum to a total volume of 6 liter, the change in internal energy is. So this is simple question. I will give you 2-3 minutes. Quickly, you can give the answer. Hint is you don't need to calculate anything. Remember, it expands into vacuum. It's written. What should be the answer? So this is related to ideal gas is expanding isothermally into vacuum. So once there is a vacuum, there is no external pressure. Okay. So whatever the given ideal gas does work against the external pressure. If it is external pressure is 0, your work done is 0. The answer is 0 joule. Next question. A hypothetical gas expands adiabatically such that its volume changes from 0.8 liters to 27 liters. If the ratio of final pressure of the gas to initial pressure of the gas is 16.81, then the ratio of Cp by Cv will be. This is also simple question. Given things are volume V1 is given, V2 is given. (27 liter). Ratio of final pressure and of the gas to the initial pressure. Remember, this is a final upon initial pressure, means P2 by P1 is given, it is 16 by 81. Fine. So it is written in the question that it is adiabatic. The expansion is adiabatic. So we know PV is to gamma is constant. We need to calculate gamma. P1 by P2 is equal to V2 by V1 raised to gamma, and P1 by P2 is P2 by P1 is given. So we'll do the same according to V1 by V2 raised to gamma. P2 by P1 is given 16 by 81. V1 by V2 is given that V1 by V2 what we get 8 by 27 raised to gamma. I will write it here. So if you see, we can write 16 as 2 raised to 4. Fine. 8 to 16, and this is can be read 3 raised to 4, and this is nothing but 2 raised to 3 and 3 raised to 3 thirds cube. So we will having 2 by 3 raised to 4, 2 by 3 raised to 3 gamma. So this is the same. 2 by 3 is 2 by 3 same. We can equate powers and nothing but 3 gamma is equal to 4. Gamma is equal to 4 by 3. Fine. 4 by 3 answer is 1. So this is the last question. A sample of gas at temperature T is adiabatically expanded to double its volume. The work done by the gas in the process is gamma is given 3 by 2. This is also a little tricky question. So we'll do. So we know initially what is the work done, adiabatic work done. Let's extract first what is the given. So double the volume. The sample temperature is T. The T1 is T, and it is adiabatically expanded to double its volume. Means the V1 is V2 is twice the V. Okay, and the work done by the gas in the process is, we need to calculate the work done. So we know the in adiabatic condition work done is CV into N CV T2 minus T1. And what we need to calculate CV. Gamma is given. We need to calculate CV. CV can be calculated as gamma is Cp minus Cv. We have Cp minus Cv is equal to R. If we divide both sides by Cv, Cp by Cv minus 1 is equal to R by Cv, which this will give you gamma minus 1 R by Cv, and Cv we can write as R by gamma minus 1. First thing we get this Cv. We need to calculate first, and T1 we know, V1 V2 we know, the relation between V1 and V2 we know. We can calculate what is the T2. We know T, oh sorry, we know T2, we need to calculate T2 and T. So I will take a new TV raised to gamma minus 1 is actually constant. But finally, T1 by T2 is equal to V2 by V1 raised to gamma minus 1. We need to calculate T2. We can write as, we can write T1 is T, as we know. T2 we need to calculate, and V2 is twice the V1, 2V1 by V1 gamma minus 1, which gives you, I'm writing here, T by T2 is equal to 2 raised to gamma is 3 by 2 minus 1 is raised to 0.5. Okay, so what we will be getting here is, so 3 by 2 minus 1 is 1 by 2, is nothing but root 2. Okay, T by T2 is root 2, is nothing but T2 is, if you rearrange it, T by root 2. Fine. So we got the T2, and we need to calculate, then put it into this equation. So in the question it is not given an R. So CV dt we can check. WCV is CV is R by gamma minus 1. T2 minus T1. T2 is T by root 2. minus T. Fine. And gamma minus 1 is nothing but 3 by 2 minus 1, which is 1 half, and R divided by 1 half will be 2R. 2R T by root 2 minus T. And you can take this T common outside and multiply by 2, which will give you RT into root 2 minus 2. Fine. RT into root 2 minus 2. So A will answer. As we know that this is for chemistry perspective, this answer will be this. In physics, it will be this, because the work done sign is different in different streams. So don't take you just uh, you just know that in chemistry, work done by the system is actually negative. Fine. How we can remember this? If we calculate every sign of your thermodynamic system according to in considering system as your center. If system is doing work, it is losing heat, means that work must be negative. If some heat is added to the system, means system is gaining something. If it is gaining, means it is positive. You can remember in that way. So in chemistry, we use system centric approach. Okay. Yeah, answer yes, A. Fine. So thank you for attending the session. We'll meet in next week, Tuesday, on 7 to 9. Thank you very much. I will end. I'm ending the call.